In this video, we will see how to make or how to form an equation of a plane for certain conditions that we are given. This video will be the first part of this, and we will have in the second video, the continuation. So what are the things that we're going to consider here will be illustrated. But before we go into that, I want to explain to you what's a normal to the plane. A straight line which is perpendicular to a plane is called a normal to a plane. So we would be using this. So that's why we're defining this. So any line which is perpendicular to a given plane is called a normal to the plane. Now, a plane is uniquely fixed if any one of the following is given. So we can define a plane if any of the following is given. So we are going to see some of the conditions. The first condition that we would see is a unit normal to the plane and the distance of a plane from the origin. What does that mean? We are given a unit vector here, which is d cap, which is normal to the plane. All right, so it's perpendicular to the plane. And also, we are given the distance from origin to the plane as p. All right, so how do we define a vector equation of a plane in normal form for this condition? So the theorem says the equation of the plane at a distance p from the origin and perpendicular to the unit normal vector d cap is given by this, or dot product with d cap is equal to p. So it's very simple. So you have p here, which is the distance from origin to the plane, and you also have any given point on the plane as p, and you have the normal to the plane as d cap. Great. So when you're given these, you can define the plane using the vector equation, which is r vector dot product with d cap is equal to p. I'll briefly explain how we derive this formula. Now, you can see that OA can be defined as P d cap because this vector OA is parallel to D, because OA will be perpendicular to the plane because it's the distance from origin to the plane, so it has to have should be perpendicular here. So this should be parallel to d cap, and d cap is the unit vector. Therefore, p times d cap will be your OA vector. Similarly, if you take any point p on the plane and define the vector OP as our vector, then your AP vector can be defined as R vector minus PD cap, right? Now, we know that your vector AP is perpendicular to the vector d cap, so, or to the vector PD cap, all right? So, this dot product with this vector will be 0. So, we can say P d cap, which is our OA vector, or you can say OA vector dot product with P AP vector is equal to PD vector dot product with R cap or R vector minus P d cap, and that's equal to 0. You can further rearrange this as R minus P d cap dot product with d cap is equal to 0. I'm just removing the p from here. Then further, you can write as R vector dot product with d vector, or d cap here, sorry, is equal to, if you take this, d cap and d cap will become 1. So you'll be left with just the p. So this will be equal to p. Hence, that's what we have here. just a short illustration. Next, let's see how to get the Cartesian equations of a plane in normal form. So, if L, M, and N be the direction cosines of d cap, so we have our d cap, the direction cosines are L, M, and N. So if we can define d cap then as L, I cap plus M, J cap plus N, K cap. We know that if we use the direction cosines and form the vector, then it is a unit vector. Therefore, replacing this in our formula here, you will get this as, replacing this into this, you get R vector into L I cap plus M J cap plus N K cap is equal to P. Further, the point P is X, Y, and Z. So further, expanding our R vector as Xi cap plus Yj cap plus Zk cap, and replacing this equation, we get the form as Lx plus My plus Nz is equal to P. So that's the Cartesian equation of a plane in normal form. So the second scenario that we would look at to form the equation of a plane is we're given a point of the plane and a normal to the plane. Let's remember, in the first condition, we had the normal to the plane, but we had the distance of the plane from the origin. But here you're given a point of the plane and a normal to the plane. So what would be? So here we are given the point A and you're given the normal to the plane. So when you're given like that, what would be your equation? So let's consider a plane passing through the point A. So that's a point A which is given to us with position vector A, and N is a normal vector to the given plane. So N is a normal vector. So let R vector be the position vector of any arbitrary point P on the plane. So the P is a position vector, or the point of a position vector, which is R vector. Now AP is perpendicular to N vector, or AP vector. If we draw from A to P, then the AP vector will be perpendicular to N, because N is perpendicular to the plane. So we can say that AP vector dot product with N vector will be equal to 0, which gives, replacing AP as R minus A vector, because at the point P we have R vector and at the point A we have vector A. So AP vector can be rewritten as R minus A vector dot product with N is equal to 0, which is the vector form of the equation of a plane passing through a point with position vector A and perpendicular to N vector. Further, we can add a note that we can rewrite this by expanding it. R dot product with N is equal to A dot product with N. Now A and N are known to us. The position vector of A is known to us and the normal is known to us. So we would be able to find this value. So replacing this with a scalar quantity Q, because the dot product will be a scalar quantity with a Q, then you have R vector dot product with N vector is equal to Q, where Q is A dot product with N vector. Let's further find the Cartesian form of the equation. So we have found this as our vector form of the equation. So to go into the Cartesian form of the equation, let's define A, B, C as direction ratios of N vector. So for the N vector, A, B, C are direction ratios. So you can rewrite vector N as AI cap plus BJ cap plus CK cap. Why do we say this? Because we are given N vector. Then suppose A is x1, y1 and z1. Again, this point is given to us. So as we describe this point as x1, y1 and z1, then replacing this into this equation, then we can define this equation as x minus x1 I cap plus y minus y1 j cap plus z minus z1 k cap dot product with our n vector is a I cap plus b j cap plus c k cap is equal to 0. So rewriting this, we can define it as a into x minus x1 plus b into y minus y1 plus c into z minus z1 is equal to 0. So that which is the Cartesian equation of a plane normal to a vector with the direction ratios a, b, c and passing through the given point x1, y1 and z1. Next, let's look at a scenario where we know where the plane intercepts with the x, y and z axis. So let's say that the plane intercepts the x-axis at the point A, which is defined as A, O, 0, 0. Similarly, the y-axis at B, which is defined as 0, B, 0. And the z-axis at point C, which is defined as 0, 0 and C. So when you're given these points, we can define x by A plus y by B plus z by C is equal to 1. So this is called the intercept form of equation of the plane having intercepts A, B, C on the x, y, z axis respectively. Thank you for watching Math Tutorial Anand. Please like and you can comment if you have any questions, and do not forget to subscribe to get more videos like this.